So let's get started, guys. So the topic for today lecture is power law and scale-free networks. We touched upon this topic last time, and now we're going to have a deep dive and try to understand what it actually means, what this power law is about, and why it is so special. So, the story of power law goes back actually just, 20 years ago. And it started with the discovery of the distribution of node degrees on the web. In fact, there were two groups that analyzed that. The one was by Andre Broder, and he worked for IBM back in that time. And the other one was the group by Barabási Albert and his students. And Andre Broder, he was actually studying, internet as it appeared back then. And in Silicon Valley, a lot of companies were building web crawlers to do web search. At the same time, guys in Notre Dame, University of Notre Dame, which is Albert Barabási and his students, they were actually just doing research on this. And the initial concept, the initial idea was that, because the World Wide Web, it's sort of being organized by random people, putting certain connections to pages. So the expectation was that it would be quite random. And so it can be modeled by a random graph. And we're going to talk next time about, how the fact that, there is a random graph, how that fact creates a Poisson distribution. But again, Poisson or Gaussian, those distributions are usually associated with, all kind of random processes. And so the expectation was that the node degrees would be also distributed as a following Poisson distribution with some sort of average node degree, sort of average degree of a web page, and then some, pages with a higher or low degrees. And I think one of the goals was actually to find this sort of average node degree, for the web page. And then to the big surprise of the researchers, they found out that if you look, if you plot the out degrees as a function of in degree, if you put the number of pages as a function of in degree or as a function of out degree, you all of a sudden, instead of having that Poisson type of distribution, you'll be having this kind of pictures. Now, this is a log-log scale, and we'll discuss in a minute why that scale is preferred. But if you see here on the horizontal axis, this is logarithm of a node degree, and this is how many pages. That's sort of the overall, the very beginning. And people previously, obviously networked with this type of distribution existed before, but, people never sort of paid a lot of attention to it. And on one hand, on the other hand, people never had such big networks at their hands to actually notice such a, difference in behavior. And we're going to learn in a few minutes sort of what make this network so special and why we call them scale-free. So just a quick reminder, we talked about it last time, and I hope you remember it, that, when we talk about networks and we talk about nodes, and there is a node degree, which is just a number of nearest neighbors, and the degree distribution is calculated as the ratio of the number of nodes of that particular degree divided by the total number of nodes. Right, and sort of that's what it is. It's a discrete distribution because obviously nodes have discrete values. Node degree is a discrete number, right? And so that's why it's discrete distribution. Now, you pick up a network, and you will actually see a lot of this network. This is called Karate Club, Zachary Karate Club network, and this is a degree distribution for this network. And it just by looking at this, actually this one is plotted on the y-axis, I don't put this distribution. It's actually just a number of nodes. You can do it that way, or you can actually put, if you want, you can normalize and put probabilities. But right now, this is just a number of nodes. So there is one node with degree 1. There are 10, actually 11 nodes with degree 2, and so on. That's how you read. And then there is here, there is one node with degree 16 and one node with degree 17. So it's quite obvious. Okay. So moving ahead, doesn't let me do it. So if I take a bigger network, for example, network like this, and it doesn't have to be connected, and it looks like a mess, so it's actually pretty hard to analyze it this way. But if you look at it, we can plot a degree distribution, and again, you will have a, here it's on the y-axis, this is a probability. On the x-axis, these are node degrees, and in that network, we actually have some nodes with degree 118. A majority of the nodes are low degree nodes. And you notice, very, very pronounced shape with a quick drop, that's sort of an exponential type of a drop. Now, keep looking at this types of distribution. Going for even bigger, even larger network, you realize that this type of distribution, you can only see it, the very, very steep drop, and you will not see anything literally, right? It's a sort of elbow bend here on the left-hand side, and you don't see anything. But then for this type of distributions, what you do, you take logarithm. And when you take logarithm, if it is a pure power law, and as we discussed previously, power law means here it's no degree to some power, and the power here is minus gamma. Then if you take logarithm of that, well, it's going to be a straight line if it is plotted against logarithm of the degree of the node. Now, there is one thing that that can look slightly strange on this picture. And if you guys look at this, does this picture on the right, does it make sense overall? Does something look strange? Does anything look strange? So this part, right? You actually here, you see those steps, which kind of bizarre, right? On one hand. On the other hand, if you actually think about what this means, that's the way it actually should be, because on the y-axis, we're plotting probability of a particular node degree. And since node degrees are integers, right? And this probability is really just the number of nodes. The probability is the number of nodes of the degree, right? Divided by the total number of nodes. So this is really, it's normalized integers. And they start with, if there is only one node with a degree 1, and then there is a node with, and then there are 2 nodes with some other degree and 3 nodes of another degree, well, then you'll have here 1, 2, 3, etc., right? And then it is normalized to be a probability. And so what this means is that we have literally one node with degree probably, I don't know, 120, and another node with degree 140, and then one node with degree, well, somewhere close to 200, probably 170. And then we have 2 nodes with degree, whatever the degree is in here, and also 2 nodes with a little bit higher degree, et cetera, et cetera. So, so when you plot this type of data, that's what it looks like. Okay. Now, if this was a perfect world, and if it was really pure power law distribution that you can describe by the log, well, it would be a straight line. Though we realize, but if you try to draw a straight line, well, there are multiple ways of doing this in here. and later on in the lecture, we'll find out which one is better, right? But if I just plot it this way, it's actually very hard to map and match some straight line. And so it's not obvious what gamma coefficient is going to be for this picture. But that's something we're going to learn how to deal with. Okay. So, and here I just zoom in into that and into the same distribution that I just showed you in the previous slide. So you can see that every node, every point here, every point corresponds to you know, the number of nodes with certain node degree. Okay, so let's see how we can actually represent this distribution. Again, you know, in real life, k here is a node degree, and so it's a natural number. Gamma is a real number, and so pk it's just you know, c, where c is some normalizing constant, because p we want p to be a distribution, right? So it is some normalizing constant. And k to the power minus gamma. And yes, if I take logarithm, it's going to be log of p of k minus gamma log k plus log of this constant. So in order for p of k to be distribution, we need to normalize it. So normalization means that the sum of p of k's, or probabilities of nodes to be of certain degree, has to be equal to 1. Well, then we do this summation, and this sum, k from 1 to infinity, k to the power minus gamma, has a name. It's called Riemann zeta function, right? And so that's just sort of the way it is defined. And then we can just write a concise form, p of k as k to the power minus gamma divided by Riemann zeta function for that k, for that gamma. All right, now this is sort of, you know, very straightforward, and with a discrete distribution, that's what you get. Now, the problem of working with this as is that when you have summation, it's actually very hard to, you know, do, you know, actually to calculate those things, right? It's much actually easier to work with integrals instead of working with sums. And we're going to explore the properties of the the power law networks actually through the what's called continuous representation. So the idea is that, and this is not sort of unique for power laws. It's quite common way to deal with the problems where you have sums, is instead of talking about a discrete distribution, we for a second gonna assume that k, the node degree, can actually take continuous values, right? Can be a real number instead of discrete number, instead of integer. And so that's going to help us to understand better properties of this distribution. All right. So now look, if I if we do this, then so that's the distribution, right? It's sort of the same, but then for normalization, instead of using summation, we put an integral, right? Because now k can take any real value. And then something we need to pay attention to is that we're actually going to start with some minimum value k. Well, why minimum value k? Well, because again, in, you know, sort of if it is you know, real network, well, you start from k most likely equal to 1, right? If you have nodes with a degree 1, and we're not taking into account disconnected nodes or whatever the minimum node degree present in the network. We also need to have this from the mathematical point of view, that because you know, we have here k to the power gamma, you know, k equal to 0, it just doesn't work here, right? It diverges. So then we can actually normalize, we can calculate normalization factor, right? And this normalization constant will be gamma minus 1, and it will depend on this minimum value that we have in the network. And so then we can represent this power law through this normalized probability distribution function. All right. So you might actually ask, so why bother? Why are we even looking at this? How is it helpful? Let's take a look at, in a few following slides. So what we have on the left-hand side, and I showed this picture before, on the left-hand side, we have an example of this Poisson network, or the network that has been created by just randomly connecting nodes with edges. On the right-hand side, we have this power law degree distribution, right? And if I look at the drawings, then the dark color, purple color, is the power law degree distribution, and green, this is Poisson. And what you can easily notice, of course, that on the left-hand side, and this is sort of obvious, on this side, we clearly have many more nodes with low degrees than Poisson distribution, right? But this is not the most striking feature. The most striking feature is actually hidden in here, in this tail, which we don't see on this picture. But if we look at the logarithmic scale, we clearly see it, that for power law, we do have, for large degree nodes, we have much higher probability of the existence of those nodes compared to Poisson. Now, why is this important? Well, because when we have larger graphs, this becomes extremely obvious. Let's say if we look at the graph of the size of the internet, and which is at this moment is probably like around trillion nodes, which is 10 to the 12th. So if we look at that size, then with Poisson distribution, the probability, for example, of having a node of size 100, right? So which is not that large, right? It's just 100 connections. It's actually like around 10 to the minus 4. Now, if I kind of continue this down, the probability to have a node of size of 100 with Poisson distribution is in fact 10 to the minus 94. So it's just not going to exist with that distribution. And if we want to estimate how many of those nodes, yeah, well, there is an average number of nodes with that degree or above, multiply the probability by the size of the internet, which is 10 to the 12th. And if you get 10 to the minus 4 times 10 to the 12th, it's going to be 10 to the 8th number of web pages with a size of at least 100 links and more. But in Poisson distributions, they will just not exist.
Sorry,
and we do know.
Please repeat this thing with Poisson distribution. Why we use Poisson? Because as I remember, we needed to say like the probability of happening something m times out of n. So why we compare to Poisson?
So next time we're going to go into this in depth on the next lecture. But the reason we're comparing to Poisson that because if the network is formed randomly means you have a bunch of nodes, and then with some fixed probability, any two nodes are connected or not. So pretty much the edges distributed randomly. Then we're going to show next time that the degree distribution in that network will be Poisson. Okay? And that's why we're comparing it Poisson, and that's why people were expecting it to be Poisson. And the whole point here is it is not, it is very far from Poisson, and there are, with this power law, there is a pretty high probability of having very large nodes, while in Poisson, it is very, very small probability. And that's what this, that's why I'm paying attention to this tail, right? That Poisson here decreases really, really fast and just does not allow existence of the large nodes, right? And again, you cannot see it on the regular scale, but it's very obvious on logarithmic scale, right? So Poisson drops much faster than power law. And again, we're looking at the Poisson because if you have nodes connected at random, then the node degree will be distributed by Poisson distribution. Make sense?
Yeah, kind of.
Okay. Well, next time we'll talk about Poisson distribution, and so you will see yourself that random networks they are distributed with the Poisson distribution. Okay. So can we actually, since now we know the distribution, the form of the distribution, and we know the numbers, right? Can we actually calculate some properties? So one property we can actually calculate easily is the size of the largest node, right? So if nodes are distributed by Poisson, by power law, well, actually by Poisson too, but we're interested in power law, we can actually try to compute what would be the largest node degree in the network, depending, of course, on the size of the network, right? So the bigger the size of the network, well, the larger nodes can be present in this network. And so we want to estimate what can be the largest size. Well, the way to do this, sort of the simple way, the easy way to do it is to think about, again, the probability. And so, probability of having a node of degree greater than some maximum node degree, this probability is actually equal to the integral from the probability distribution from that node degree to infinity. Now, if I want to calculate the expected number, well, that's what it's going to be. If I want to calculate the expected number of nodes having the degree more than maximum, just by multiplying by the number of nodes. And let's say I want to, I'm just saying, okay, I want to have like the largest node possible, right? So, it's enough for me to have one node of degree more than some maximum degree, right? Then I equate it to 1. And from this, and having the equation for the distribution, we can actually calculate what would that maximum node degree be. And for example, for exponential network or exponential, like Poisson network, we realize that maximum node degree can be estimated as whatever the smallest is plus logarithm of the size of the network. But if we look at the power law network, the largest node degree will be connected with a number of nodes by this function. So it is growing really fast with the size of the network, right? Which is again very, very different compared to what you would expect in the random network. If I look closer at this, for the random network, the size of the network affects the size of the largest node degree, but very slowly. So it's growing, yes, the largest node degree will increase with the size of the network, but not very large. Now, why would I put here n-1 as a reference of the maximum node degree versus the size of the network? What kind of network will have the largest node degree n-1?
Complete.
I'm sorry, say it again.
Complete network.
Okay. So if we have like, say, 3, then, if we have 3 nodes, then the largest node degree in this complete network will be, connected to everybody except for 1, right? So it can be complete network or it can be star network. But that's sort of what's maximally possible. The point here is a scale-free network, though being quite sparse, and we'll see that, still has the maximum degree growing very fast. Again, there is a difference here. If you have a complete network, then every node degree will grow that fast, right? But we don't have a complete network, right? And so this is a maximum node degree that's possible. And so which means there are some special nodes whose node degree is growing very fast. I think good mental picture here is those celebrities, right? Think about Facebook or any other, or like Twitter or whatever. There are a lot of people there. Most of the node degrees are small, not very many people following just sort of random every Joe, but a lot of people following the celebrities. And so with this type of structure, some nodes have a chance to grow very, very large. If the connectivity is random, that's not going to happen. Okay. We're going to talk about a model that actually creates this phenomenon. One of the models called preferential attachments, why those nodes actually accumulate a lot of links and very high degrees, but we're going to do it in a couple other lectures. Here, the point is sort of from observing the graph, you realize that in the power law networks, the degree of the largest nodes growing very fast and can be very large compared to random network. Now, but that's not all. There are actually other very, very sort of specific properties, I would even say strange properties, that power law possesses. So let's take a look at this. Well, this is our distribution. And well, we have this restriction, and that's normalization. Let's try with this distribution to calculate average node degree, right? I mean, when you have a finite network, finite number of nodes, how do you compute average node degree? Well, you just take node degrees of every node, add them up, divide by the number of nodes, that's average node degree, okay? Now, let's assume for a second that we have an infinite network, right? The network of the infinite size. Let's try to see if we can calculate average node degree here. And what's going to be happening is, as we notice, for example, on a random network, the maximum node degree grows very, very slowly with the size of the network. At the same time, in the power law network, it grows pretty fast. So that leads to very strange behavior. It leads to the following situation. We can calculate average node degree, mean value, which is this integral, right? Now we take this distribution, plug it in. But now you have this integral. When will this integral converge? So that's infinity on the top here. Do you guys remember when will this integral converge? This type of an integral?
When gamma is less than 0?
Actually, if gamma is less than 0, right, this is negative, so it is becoming
yeah.
Gamma squared, and infinity will diverge. So what we need for this to converge is for gamma, for this to be at least 1, because if it is, so if you have, say 1 over k, right, then what's the integral from 1 over k? Oh, come on, what you need to do, what function do you need to differentiate to get 1 over k? Okay, don't embarrass me.
Logarithm.
Don't embarrass me, people.
Logarithm.
Logarithm, right? It's logarithm k. Now, if I go to infinity, what's logarithm of infinity?
Infinity.
It's diverging. So if I take 1 over k, that integral diverges. But if I take 1 over k, for example, squared, then the integral will be equal to 1 over k, and at infinity, it is 0, so it converges. So we need to make sure that whatever is here, right, is greater than 1. Otherwise, it diverges. And so gamma minus 1 to be greater than 1, well, gamma has to be greater than 2. That is sort of a little bit strange, right? Why would we care what happens when the graph is infinitely large? It looks like a sort of math that we shouldn't care about. Well, in fact, we should care about it. It leads to a few very interesting properties. We're going to see them in a second. But before going there, let's look at the second moment. And the second moment, why do we need second moment? Well, because if I want to have a look for the standard deviation, right? Then it is the difference between the squared first moment and second moment, right? And well, if you actually just follow the same logic as we just did before, and we look at this integral, for this integral to converge, gamma actually has to be greater than 3. Now, remember what gamma is. Gamma is this coefficient in the power law. So pretty much what I'm saying, if gamma less than 2, well, the average really doesn't exist for large networks, which is bizarre, but that's what it says, right? And if gamma is greater than 3, then fluctuation exists, but if less, they do not. So there is something strange happens, some strange things happening in between gamma 2, right, and gamma 3, because in interval gamma from 2 to 3, this exists, but this does not exist, right? This diverges. Less than 2, it all diverges. Greater than 3, it all converges, right? We're going to explore this in a second, but just keep this in mind right now. So what does this actually mean, right? On the previous slide, we looked at at the size of the graph going to infinity. In real world, well, the size doesn't go to infinity, but you can take graphs with sort of increasing number of nodes, right? The graph can grow, or you can take larger and larger samples. And so what this shows is the following, that for graphs, and here, I copied this figures from some other paper, and so this is gamma. This is our gamma. This is our gamma in the equation, right? So when gamma is 3, for example, here it's 3.1, which is gamma above 3. What you have here is average, this thing, and variance. They both pretty much don't change. When gamma is in between 2 and 3, which is here, it's 2.5, the average stays stable with the size of the sum of the graph, but the variance increases. And if you look at the below, they're both increasing. Now, why is this important, right? What the hell does this mean? And why do we care that this does not increase with the number of nodes and this increases? Well, the reason is the following. If we take, and again, I'm coming back to this random network. If we look at the random network and we look at the Poisson degree distribution, right? This is what it looks like. Sort of this nice, bell shape, which really tells us that there is the highest probability of a node to have certain degrees here, right? This is average node degree. And all other nodes have degrees that you take this average, plus minus sigma. And that's what we usually get used to in pretty much in our everyday life, right? There is this average value, and then there is this, standard deviation from it, to the left, to the right, a little bit larger, a little bit smaller, but that's where all the data points are allocated, right? That's what you would expect from, random graph. And so, which actually means there is a scale that exists there. The scale is that peak in the distribution. So the scale can be, 10 nodes, and that means, majority of the nodes have degree 10. There are some nodes that have degree maybe, 11, 12. Some nodes has degrees 6, 7, but there are fewer of those. And so there's this characteristic size, which is, 10. If you have a grid, right, a lattice, perfect lattice, every node has a degree, for example, 4, right? Every node connected to, it's 4 neighbors. Well, the characteristic size is 4, characteristic size there for the node degree. We talk about the height of somebody in the class. Well, the characteristic height will be, I don't know, 1 meter, 70 centimeters, and everything else will be around it. So there'll be a scale. So this 170 will be a scale, and then you can compare everything to it. And that's what happens with Poisson. Now, with a random graph, with a power law graph, that's not the case. With power law graph, we just saw that, for example, when gamma is in between 2 and 3, and that's why I point your attention to that, the average, does exist, but then the fluctuation is infinite. So what it means is, in plain English, well, there is no particular size with respect to which we can anchor everything else. And so that's why it's called scale free. So there is no this peak in the distribution. There is no particular size which is common to all the nodes in the graph. There are nodes with low degrees, there are nodes with high degrees, but there is no this particular size, and that's why it's scale free. There is no scale. And that happens because, yes, you do have an average, but nodes within the graph can be much, much larger than that average, much, much smaller, and that's okay according to the distribution. And so the scale-free property comes exactly from this, from this fact. That's what it's called, right? That's why it's scale-free. So it is scale-free because there is no scale, there is no sort of average. So there is an average, but there is no degree with respect to which most of the nodes have their degrees, right? So the node degrees are distributed. There are nodes with large degrees, small degrees, but there is no characteristic degree like you would have with Poisson distribution. Does this make some sense? Okay, so that's what scale-free is. Now, what's interesting to observe is sort of, what happens in the real world, in the real networks. There are a bunch of networks shown here, number of nodes, number of edges, average degrees. And for some of them, you can calculate the fluctuations, right? K out, gammas, and you realize that you're going to have, pretty large K squared. Now, it's probably worth looking at this on this picture. So what I have here is on the x-axis is node degree, right? K, average node degree. And on the y-axis, because it's a graph, right? And we actually have this experimental graphs, they do exist. We can actually just take and calculate sigmas, right? Because sigma is defined as average K squared minus K average squared. So we can actually calculate it.
Excuse me, can you please let in one person?
Yes, sure.
His Zoom just fallen. He tries to get in.
Yes, yes, sure. Guys, you wanted to ask a question? Okay, sorry, I'm lost. Did you guys want to ask a question? All right.
No, there was no question. Someone was asking to let people here.
To let people in.
Yes, we're
Okay.
waiting in the waiting room.
We are in. Thank you.
Okay.
Thank
all
you
right,
so much.
Okay. Sure. All right. So what I was saying then is that look, here we can calculate the average. We can calculate sigmas because sigmas is just defined as average k squared minus k average squared. And for any real graph, we can actually just take and compute it, right? Just sort of by adding things up. Now, when we do this, that's what we get. So on the x-axis here, we have average node degree. And on the y-axis, there is a sigmas, right? The fluctuations. If the graph is, regular graph, or if the graph is random, like Poisson graph, you will have this distribution. You'll have sigmas, of course, much smaller than average k, right? That's typically the case. So you have, the height, and then the height, and within the class, the height will fluctuate. But if the average height of an average person is, 170, well, you'll have fluctuation plus minus 10 centimeters, right? Or maybe plus minus 20, but that's about it. What we observe in the real world networks is that, you get, for example, average node degree in the network is 6, but the fluctuation is 15, which is much larger than 6, right? Which is bizarre, because you will get, then it means, you might, if the distribution was Gaussian, you would get like negative node degrees, or you can have an average node degree like 4, and then in World Wide Web, you get, up to 40 fluctuations if you just calculate those fluctuations. So again, this sort of strange pictures, they happen because the distribution is not Gaussian, and you cannot, the sigmas here, they really do not make any sense. And that's, again, this notion of scale free. So k is usually scale because you have those sigmas, and all the node degrees are around this k average. And what this shows that in the real world network, it's not so, and that's why there is no scale there. We saw those pictures before. Now, this is quite also interesting discussion. 20 years ago, and when, Barabási was making, his first papers, and people were studying this, there was a lot of discussion about, okay, here is our scale-free network, right? This is a straight line, this is a straight line. So people were discovering, it was a hype in some sense, people were discovering more and more and more and more of those scale-free networks. And pretty much we're saying, okay, look, it may be not completely scale-free, right? But, maybe there is a part here which is scale-free. Now there is, 20 years later, now there is some pushback on this, saying like, yeah, this scale-free networks, they're universal, but not as universal that, scientists wanted to think about them 20 years ago. And yes, they might be quite universal, but the most likely what we have is that there are certain regions where you get the scale-free behavior, but then there are some other regions that deviates, and there is no pure scale-free behavior there. And so in some sense, there is a feeling right now among the community, research community, that the scale-free property is a little bit overrated. And so, in the real world, there are some networks that do possess this property, but not all of them have it. At the same time, from theoretical point of view, this is a really beautiful math showing that, yes, there is this sort of interval of parameters where there is this sort of unique properties of the system. So to sum up with the scale-free networks, what we have is we literally have three regions, right? We have a region, now this is gamma, right? This is this P K minus gamma, right? So this is this gamma, this is this power law coefficient. And this is 2, this is 3, those magic numbers. And remember that we saw in our computations that you need to have gamma at least equal to 2 for average K to be finite, but then K squared diverges. And when gamma exceeds 3 and we are in this part, both of them are finite. And so this part, this region from 2 to 3, that's what's called the scale-free regime, right? Or this is where most of our scale-free networks live, in between, with this gamma coefficient in between 2 and 3. The most weird, the most bizarre part is here, when gamma is less than 2, right? Because here you will get average K diverging and average K squared diverges. So this is very strange. In fact, that really means, if you try to go back through our calculations, that the maximum node degree, remember it is 1, we estimated it was n 1 divided by gamma minus 1. Well, if gamma is less than 2, that means, maximum node degree grows faster than the number of nodes, which, impossible. And there are some other reasons, except not only this, but there are some other reasons. And, pure networks, power law networks do not exist in this regime. So you just don't have it. Now, you can still get a network and you can still calculate those, the coefficient, and you will get gamma less than 2. But that means it's not a pure power law network. It means, there is probably part of the network that has this distribution and the rest do not. But you cannot have a pure network, pure power law network with gamma less than 2. So this is sort of anomalous regime, it's physically impossible to exist. Now, this part is called scale-free regime. And on the right-hand side, this is more called random regime. There is sort of, it's more, again, more standard story. And so this is this fascinating part, the scale-free property. So as I mentioned, today there is some skepsis about the fact that there are a lot of networks that, like all networks in the world, are these power law networks. And again, back in 2000, when this has been discovered, people thought that most of the networks are power law, and that's why they wanted to pretty much quote every network as a power law network, right? So now it's not exactly the case. And there is this paper by Aaron Closet. He is a scientist from Denver, who looked actually at the pretty big collection of power of networks. And in fact, those networks are all available on his website, so you can download it, try yourself. And so he characterized the networks by this degree of scale-free property. And in fact, this, in his characterization, strong scale-free and strongest scale-free, these are two sort of those two things, that's where for the network, the gamma is between 2 and 3. And so, he went through all the networks he had, which is, more than 1,000 different networks. And he realized that, only a handful of them have the node degrees have the gamma in between 2 and 3. And there are quite a few networks with a much larger gamma, or, almost no network with a smaller gamma. And so he pretty much claims that, look, the scale-free networks, yes, they do exist, but there is not that many of them out there, right? It's not all the networks out there that scale-free. If you're interested, I recommend you to sort of Google him and the scale-free networks in the real world, and the guys were arguing on Twitter as crazy. So the amazing part of internet that it all now for posterity, right? So you can actually search and see all the arguments people present for and against the fact that all the network in the world are scale-free. So bottom line, today we think that there exist scale-free networks. Not all the networks in the world are scale-free, but there are quite a few of them. And those networks have this power law degree distribution. And for those networks, this gamma lies within this regime between 2 and 3. Then the question is, okay, if they exist and if they possess this scale-free property, can we find gamma? How can we actually calculate this gamma parameter, and how to do it the right way? We're going to touch upon this a little bit, and then you're going to work on this during the lab session. There are several ideas. So one idea is to actually plot the things the right way. We saw at the very beginning that it is not very easy to draw the line, because if you do look at the log scale, you think like, okay, well, I'll draw a line, and then the angle for that line, that's your gamma coefficient, and I'm done. Well, the question is, these nuances of how to draw the line the right way, it's not very easy. And so, but there are ways to make this work really easily and really nicely. And it also lays in the fact that we have this power law distribution, because look, this is a power law distribution, right? P of k, and this is a gamma that we want to find. Let's look at the cumulative distribution function. Well, cumulative distribution function is just an integral of this, right? From 0 to k. There is also what's called complementary cumulative distribution function, which is a probability that your node is greater than given degree k, okay? And you can calculate it as an integral from k to infinity, p of k dk. So to estimate this, we calculate this integral. And again, it's a cumulative, which means, you look for all the nodes, you add up all the node degrees that are greater than k, right? And in fact, you want to do, you can use these tricks all the time when you have this type of noisy data. So why would this work? Why would this work nicely? Well, look, if I take this distribution and plug it in here and take the integral, you realize that you get pretty much the same shape of distribution, right? Well, the constant, who cares? But here you get k to the power minus gamma minus 1, and here it's k to the power minus gamma. And so if I take log, well, I again get a straight line. Log of instead of taking log from a power law, I take a log from cumulative distribution function and draw it as a function of logarithm of node degree. It's going to be again a straight line, but the angle, the coefficient, is gamma minus 1 instead of gamma. Now, why would I want to do this, right? Why would I bother? Well, here is the answer. Let's take a look at this. Well, this is a distribution when I do it, just plot it as is, right? I take it on the left-hand side, I'm sorry, on the y-axis, there is a probability on, x-axis, that's your node degree, right? Okay, I can be smarter and I can take this and plot this in logarithmic scale, right? So this is logarithmic scale. I plot it as a logarithmic scale on both axes, X and Y. And then, well, then I get this distribution, and I need to draw a line. Now we understand why there's a sort of staircases there, right? That's the right thing, they should be there. But now when I have this picture, how do I draw a line? I can draw it this way, I can draw it this way, I can draw it, well, probably this way. Which one is the right line? It's hard to say. But then what happens is, if instead of doing it here, you can actually calculate cumulative distribution function. And cumulative means you just calculate number of nodes with, not with that node degree, but number of nodes with that node degree and above, right? This is called, again, complementary cumulative distribution function. So you calculate the number of nodes not at that degree, but number of nodes at that degree and above. And which means, you know, for the node of degree 1, it's all the nodes. And then you plot it, well, you get very, very nice and smooth picture here. And there is much better chance that you will draw the right line. Now, when you got this line, the slope of this line will be gamma minus 1. The slope of this line is gamma. And so when you get this, you just correct it by 1, and that's your slope. Okay, so that's one way of doing things, doing it quickly and dirty. Now, there is still a question. Even if we have this nice and smooth line, there's still a question. Okay, maybe I should draw a line this way, or maybe, you know, this way. You know, where will the distribution, the actual power law starts, right? I mean, by looking at this, it feels like it starts there, but maybe not. So the question is, how do I find this point from which I draw my line? Okay, and here is yet another trick how to do it the right way, right? Mathematically correct way. So we can think about, you know, data points about the graph as being generated, you know, from the distribution, from power law distribution in this independently sampling the distribution, right? So we're talking right now about the graph, nodes with degrees, and so we have this distribution, and we randomly sample the distribution. You know, that's our node, and get a node with certain degree. And then, you know, since it's a power law, well, here is our probability distribution. I put here x's. Ouch. We can use node degree. I mean, this is the same as k's, right? Ki's. So probability of degree ki, well, this is given by our power law. Now, if we have a sample, a graph is a sample of nodes. So we have, you know, some number of nodes, each of them sampled independently. Then the probability of this, you know, node degrees within the sample with a given gamma is given to us by the product of probability of node of each node, right? And since they are sampled independently, well, we just multiply those probabilities. And now if I want to calculate, because remember, my goal is to calculate gamma, calculate the coefficient for the power law, I can actually write down that probability of coefficient given those data points. Well, this is how it is connected through the Bayes theorem. And so what we're going to do, actually, we're using this what's called maximum likelihood estimation for the parameter, right? If you actually did some data science courses, that's the way you do it. So I have this. My next step will be very simple. I'll just go and do log likelihood, right? I take logarithm of this, and then I will differentiate it with respect to the parameter gamma. And if I differentiate it with the parameter gamma, well, I get the formula for it. Okay. And I can also, you know, estimate the error here. Now, everything is nice, except one little fact, which is I need still put here in this estimate, I need to put minimum node degree, minimum value, right? And obviously this estimation will depend on this X-min. So far what I literally done, if I go back here, I done a nice way to map a line here, but I haven't figured out where to start yet, right? Because if you start here, that's going to be the picture. If I start here, maybe this is going to be the picture. And if I start from this point, this is the right line. So I calculated the way through maximum likelihood, how by having those data points to estimate, the slope, but I haven't figured out yet how to select this, K or X min from which to start my computations, right? And so here is yet another technique how to do this. So here we are. The goal is to determine this. And that's how here's how we're gonna do this. We're gonna use what's called Kolmogorov-Smirnov test to compare cumulative distribution function that our model generates and cumulative distribution function that we have from the data. And so the idea is the following. We have cumulative distribution functions, and here is, let me change the color. Let's say here is experimental one, from the data. This is a distribution function. And this distribution function is cumulative distribution function. That's why it's smooth, right? That comes from our model. So what we're going to do is for every step of the distribution function, for every node degree, we'll compare the distance, the difference. We'll calculate the difference. And Kolmogorov-Smirnov test tells us to pick up the point where the difference in between distributions the largest. So we look for the differences in between distributions at the different node degrees, and this is node degree, at the different node degrees, and pick up the one that is largest, okay? And that's what we're going to do is we're going to go through all possible minimal starting points and try to find the one that minimizes this difference. And so here it shows, you go through all these guys and you find the minimum, the starting point that minimizes, and here it is, this one that minimizes this difference. And so by doing through our starting points, we're actually selecting the point from which you start mapping the line. And so this example shows you that this is a point from which the distribution looks, which is where the distribution fits the best for the power law. So it's not from here, it's not from here, but it is from this point. And the way to find it is by using this Kolmogorov-Smirnov test. And on the discussion on the lab session after the lecture, you'll have a chance to practice this. Okay. So that's actually it for today. What we learned is that there is this very special power law distribution, and that distribution, so strange that it does not have particular scale, and that means there is no particular characteristic size, node degree around which every other nodes is kind of clustered in the sense of, there are node degrees close to it, but node degrees are spread all over the place. There are quite a few nodes with large node degrees, quite a few nodes with small node degrees. If you look at the power law distribution, at the function p equal minus k, k to the power minus gamma, this gamma parameter usually, for scale-free regime takes values in between 2 to 3. And in that regime, in this strange regime, the average converges, but the fluctuations diverge, right? And that's why it's called scale-free network. And then we also learned the way to actually calculate that gamma for the real world network using maximum likelihood estimation and this Kolmogorov-Smirnov test. And finally, it's missing on this reference slide, but I'm going to edit the reference to Aaron Closet paper on this discussion. Okay, you know, how much of the real world networks are actually scale free. They're out there, but maybe not all of the networks that we have there are scale free, but there are plenty of those. And with that, we're done. Any questions?
One small question. Could you please share with us with the presentation?
Yeah, absolutely. So the presentation, you know, the website is up and I'm posting a presentation on that website. So I'm going to do it, you know, later tonight, you know, presentation and the link to the video that's hopefully being recorded.
You mean that website on network science DS DDNS net, that one?
Well, the network, yeah, that I showed on the very first presentation. Yeah.
Okay.
Networks. I forgot the precise link, but you can ask. Yep. So we posted there, and I also share it on the Telegram.
Because I thought that you shared with us the video from the lecture, not the presentation
I'll put
itself.
there. Yeah. I'll put the link there for the slides.
Okay.
Absolutely.
Thank you.
Anything else, guys? Okay. All right. And again, sorry for this interruption, but technical challenge difficulties. All right, we're done for today. Thank you very much.
Thank you.